Hi, physics. Today we are going to be learning some simple conversions so that we can do them with our units and different kinds of units in physics. Because there are a lot of different units in physics and they mix and match with one another, and it's helpful to know how they're going to work together and how to particularly convert from one to another. So, in this picture here, I have pandas and cows. You'll notice there's a 7 and a 5, and that is because we're going to be trading cows for pandas. So right now, 7 pandas equal 5 cows. It's a little silly. It doesn't really matter. So if I want to figure out how many cows I can get for how many pandas, we're going to set it up something like this. So let's move our cow over here because pandas are cooler. We want the pandas. So let's say we start off with a number of cows. Let's say we have let's say we have 3 cows. So we're going to set it up so that cows are on the bottom and pandas are up on top. So what happens here is we have a fraction and we are multiplying by 3. And hopefully we are left with pandas. So what we'll see here is that our units of cows, they cancel. And all we are left with is pandas. Now this doesn't come out cleanly. We're going to end up with only partial pandas, which is kind of sad. So we're going to have 3 times 7, which is 21, over 5. 21 fifths pandas. So we're left with just a little bit of a panda left over. Now that's not very clean. Let's try another one. All right. In this example, we have 3 toucans equal 4 elephants. Now we're going to start off with a nice clean number of toucans. We're going to go for 9 toucans. We've been saving up for a couple years, so we have plenty. Now, just as before, we're going to take the toucans and we're going to put them underneath. So toucans go underneath and elephants go on top. And we are dividing the two, right? So our units of toucans cancel and we're left with elephants. So we have 9 times 4, which gives us 36 over 3. So in the end, we have 12 elephants. I can move this guy a little bit over. Actually, we'll just erase it. 12 elephants. So these are the basics of conversions, and you're going to have to do this with, instead of fun little clip art pictures that I have, we'll have to use actual units. So let's give it a go. So let's try it out with some actual units. We know that 2.2 pounds is equal to 1 single kilogram. All right. So let's try to convert a number of kilograms into pounds. So let's start off. I have 67 kilograms, and we want to convert that. So we want to cancel out the kilograms, and we want to be left with pounds. So we're going to multiply so that the pounds are on top and the kilograms are on bottom. So kilograms cancel, and I am left with 67 times 2.2. Plugging that into my calculator gives me 147.4 pounds. Now, one simple conversion isn't too bad, but let's try a couple conversions at the same time. All right, so let's start off with some time then, since there's multiple conversions in time. So let's say we have 2 days, and we want to know how many minutes are in those 2 days. So our first one is days to hours, and then we can then connect it to hours to minutes. right? So we want to end up with minutes. So we know that minutes needs to be on top. So we have 60 minutes over 1 hour. Then we want to get rid of hours. So we need hours to actually be on top here, and days are on bottom, so they'll cancel out. So if 24 hours over 1 day. Now I can cancel out the units even though they are on the right side and the left side. So this day cancels out with these days, and this single hour cancels out with those hours over there. So now all I do is multiply across and multiply across the bottom. So I have 2 times 60 times 24 divided by 1 times 1. So it's 2 times 60 times 24 over 1 times 1. So in the end, we are left with 2,880 minutes. In the background, you can hear my dog squeaking something. Don't worry about him. He's all good.
All right, so this is the basics of conversions. But what about when we have really big and really small numbers? That tends to be pretty hard to represent. Like, let's take the mass of the sun. Now, the sun has a mass that is 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. How many do I have so far? 3, 6, 9, 12, 0, 0, 0, 0, 0, 0, 6, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Done. So that is 2 and 30 zeros. To be honest, I don't even really remember what that number truly is. Oh, sorry. That's kilograms. That's kilograms. I gotta use my units here. All right. This is really ugly. I don't want to write out 30 zeros every time I want to represent the mass of the sun. So scientists have come up with what's called scientific notation, which you may be semi-familiar with, but here I want to help you know how to use them. So this in scientific notation will be 2 times 10 to the 30th kilograms. Much, much simpler than before. Now, scientific notation is also really good at representing very, very tiny things, like an electron. Particularly, we can look at an electron's mass. The mass of an electron in terms of kilograms is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And then it is 9109 kilograms. Again, I don't want to write out tens of zeros at the same time. So instead, what I'm going to do is I'm going to represent it with scientific notation. Okay. Now, when we're dealing with really, really tiny numbers, we do kind of the opposite. So what we're going to do is we're going to have 9.109 times 10, but it's now negative 31 kilograms. All right. So now we've seen both of these big and small kinds of numbers represented with scientific notation. What the heck does it mean? So the first thing that you should know is that when I have my really big number, right, 2 times 10 to the 30th, that is the number of times I multiply 2 by 10. I multiply it 30 times. So it's going to be 2 times 10 times 10 dot, 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 until I have done this 30 times. That's all that it represents. Now, it's a little bit more confusing, but what about the tiny number, right? So I had 9.109 times 10 to the negative 31. What happens when I have a negative? Well, if you remember anything about your exponents, you'll remember that a negative exponent means it goes underneath into the denominator. So actually what this means is that it's going to be 9.109 divided by 10 divided by 10 until I have divided by 10 31 times. Okay? This is what the negative means. All right. Now let's say I was dealing with my 2 times 10 to the 30th over here, and I wanted to move the decimal place in a particular direction. Because really all scientific notation is it's moving the decimal place over and then representing that with 10 to the power of something. So if, let's say I make the 2 times 10 to the 30th a 20, right? I have moved my decimal place once to the right. So I have essentially multiplied by my 2 by 10. And I have then stolen one of the 10s. So now it's going to be 20 times 10 to the 29th. All right, let's do the same thing with my negative exponent. So I have 9.109. And I'm going to move this decimal place once over, right? It was 10 to the negative 31. Now it's going to be 91.09 times 10, and I multiplied by 10. But since this was a negative, now I'm going to actually have to subtract, so it's going to be a negative 32, right? That's negative 31 minus 1. Up here, this was 30 minus 1. That's how I got there, right? I stole a 10. Here, I stole a 10 that I didn't really have, so it gets even more negative. Okay. Okay, so now that we know what scientific notation is and how moving the decimal place works a bit, let's add scientific notation together. So here we have 13.4 times 10 to the 12th plus 20.1 times 10 to the 11th. Now, whenever I am adding scientific notation or subtracting, I need to make sure that they have the same exponent. Okay, so notice that I have times 10 to the 12th and times 10 to the 11th. They do not have the same exponent. So what I'm going to need to do is I'm going to make sure that they are going to have the same. So the easiest way to do that is move one decimal place left or right, right? Notice they're off by 1, so I just need to give one another 10 or steal a 10. So I am going to here give a 10, right? I'm going to take one away from here and I'm going to put it over here. So I moved it to the left. Moving a decimal place to the left increases the exponent. So now I have 13.4, 10 to the 12th, plus 2.01 times 10 to the 12th. Okay, so now I can add them together. It's pretty quick. The exponents don't really work together at all. Now that they have the same thing, I'm just going to leave it that way. So all I have to do is add the numbers together. So 13.4 plus 2.01 gives me 15.41, and this stays the same. Okay, so that's how we add. Next up is division. Since subtraction is the same thing, it's just the opposite, right? We subtract the numbers instead of adding them together. We're going to work on division next. So here's my problem. I have 9.72 times 10 to the 12th divided by 3.19 times 10 to the 6th. So the first thing I'm going to do is I'm going to kind of split these two things up into different parts. So this section is going to come over here, and this section is going to come over here. So 9.72 divided by 3.19 is going to work just like normal. But my exponents are going to come over here, and we're going to fiddle with them a little bit. So what do I do with 10 to the 12th and 10 to the 6th? Well, 10 over 10 is just going to be 1, so we don't have to worry about that all much. But these two things are going to be slightly different. So it is going to be the difference between them. So 12 minus 6 gives me 6. 9.72 divided by 3.19 gives me 3.04. And I can now bring these two things together. So it's going to be 3.04 times 10 to the 6th. Okay, so notice I do normal division over here. And I don't even really have to worry about the tens here. I just subtract. So when I am dividing, I subtract exponents. This is important to remember. I would write it down. Next up is multiplying. It works relatively similarly to dividing, but it is just a little bit different. So here's my problem. I have 6.11 times 10 to the third multiplied by 9.53 times 10 to the 7th. Just like before, it's going to be the multiplication of these two pieces. So these guys are going to come over here. And then these two guys are going to come over here. Okay. So it's 6.11 times 9.53, just like normal. Okay. Which yields 58.2. All right, we know the value, but we don't know how big this value truly is. So now what we need to do is come over here. So 10 to the third times 10 to the 7th. Well, in the previous problem, we subtracted the exponents. So if you think about this one, we are now going to be adding them together. So in the end, we get 10 to the 10. So we can take our answer here and our answer here and bring it together. 58.2 times 10 to the 10. Awesome. So when you're multiplying, you add the exponents together. When you're subtracting, when you're dividing the scientific notation by one another, you subtract. Okay? All right. Let's give it a go with a practice problem. All right, this practice problem is actually one of the problems on your homework. So if you have that on you, I will pull it out. So the first problem is we want to convert 10 meters into a number of kilometers. All right, so we know, given our conversions, that 1,000 meters or 1 times 10 to the third, right? We move it once, twice, 3 times over. We get 10 to the third meters equals 1 kilometer. Okay. Now we don't have 1,000 meters. We only have 10. So we are going to have to convert this number of meters into a number of kilometers. So let's start off by bringing our meters down. There's the train. So we have 10 meters. And we want to convert into kilometers. We want to cancel out the meters. So it's going to be 1 kilometer over 1 times 10 to the third meters. Meters cancel out. We're left with kilometers. So we have 10 kilometers over 1 times 10 to the third. Not the best answer so far. We want to clean it up. So remember, we are going to take these two things. 1 divided by 1 or 10 divided by 1 is just 10. So I know I'm going to keep my 10, but I'm dividing by 3. So it's going to be times 10 to the 1 minus 3. Or actually, it is 0, right? We don't have them 10 times 10 to the something. It's just 0. So in the end, we get 10 times 10 to the negative 3 kilometers. Now that's kind of gross. I don't like that all too much. Normal scientific notation moves the decimal so that the value of the whole thing is between 1 and 10. So right now we're at 10. We want to get underneath that. So we're going to move that once to the left, which means that we add 1 to the exponent. So all we're left with is 1.0 times 10 to the negative 2 kilometers. All right? If I didn't even want it in scientific notation, I could move this over once, twice more, so that I add 2 here. So it's going to be 0.01 kilometers. So this one works, or you could have it as 10 times 10 to the negative 2. This one would also work. Okay? Now notice that's a lot of work to convert from one unit to the next. So let's try to figure out a simpler way to do this. So our next problem, we want to convert 600 millimeters into a number of centimeters. Now, if you remember your prefixes for standard units like this, you'll remember King Henry died by drinking chocolate milk, something like that. So we will remember that centimeters is 1 unit size larger than millimeters, right? If I was to write out the scientific notation, centimeters would be times 10 to the negative 2, and millimeters would be times 10 to the negative 3 in terms of the base unit of meters. Okay? So I know that I just need to move my decimal place 1 spot. And since I am moving from millimeters to centimeters, I can see that all I did was I added 1, right? I added 1 to the exponent, and this gives me negative 2, right? That gives me the centimeters. So how do I do that? If I'm going to increase my exponent by 1, right? Technically, that's what I'm doing. I'm increasing it. I'm adding. So that means I have to steal a 10 from the millimeters. So if I have 600, I need to steal a 10. I need to take it away so that I get centimeters. So all I need is 60 centimeters here. That makes it pretty simple. Okay? This is a really quick way to do it. If you want to figure out another way, maybe with a little bit more math, I can show you here. So I have a number of millimeters. I have 600 millimeters, right? Or 600 times 10 to the negative 3 over 1 times 10 to the negative 2, right? I want to get centimeters. So just to be clear, the exponent, the scientific notation, is always going to go on top for what you start off with. So since I have millimeters, I have the negative 3, and then I have the negative 2 for centimeters, which goes on bottom. So I can write that out, right? 600 doesn't change, comes down here, but I have times 10 to the negative 3 minus 2. And actually, it's a minus 2, right? I have to subtract it. And since the exponent is already negative, I add them together, and I end up with a negative 1. So 600 times 10 to the negative 1 centimeters. Look, I'm ending up with 1 spot to the right. So I'm going to move it to the left. I'm going to steal a 10, and I end up with 60 centimeters. Notice in both cases that this is going to work. All right, now I show you this second way here, this spot, because not all of the exponents are going to be literally right next to one another. You might have something like micro to picometers. Now these have exponents, if I remember correctly, of negative 6 and negative 12. So you're going to have a difference of 6. So you're going to have to move that decimal point either 6 to the left or 6 to the right, depending on which one you're moving to. So you'll have to be careful about that. But this is the basics of converting your scientific notation using the prefixes.